Hi everyone, here we are for our experiment 2, which is nitration of phenacetin. You guys have come across phenacetin if you had taken organic chemistry 1 at ACC. Remember we isolated phenacetin from I think experiment 2 or 3, that we had 3 ingredients: phenacetin, acetyl, what's the other one, acetanilide and aspirin, and then we isolated phenacetin and did recrystallization and all that. So this is, we are going to do a nitration on phenacetin. So again, the purpose for this reaction is to nitrate phenacetin via electrophilic aromatic substitution. Normally the benzene rings undergo electrophilic aromatic substitution because the electrophiles will attach on the benzene ring. Benzene ring is an electron rich species. You can consider it as a nucleophile. So if the electron is rich, you cannot have another electron rich species coming into the benzene ring, so you would go for somebody who doesn't have much electron. So we call it as an electrophile, E plus, meaning electron deficient. Okay. So the learning objectives of this experiment would be, you will learn how to nitrate via electrophilic aromatic substitution. You will also learn how to safely work with concentrated nitric acid and acetic acids. Okay. Now here is the balanced equation for nitration of phenacetin. So this is the structure of phenacetin. Oops. Okay, the first one. And then the reactants, we are going to be adding nitric acid and catalytic acetic acid, abbreviated as HOAC, and then the nitro group will add on to the author position of the amide group. Amide group is NHCOCH3 group, so it would be the author position. Sometimes you can also call it as a second position. If you give the number 1 to the carbon bearing the nitrogen, that's number 1, and then the second position is NO2. Sometimes it can go to third position too, but with the experiment conditions that we are doing here, it will only attach to the second position. Okay, so the mechanism of the reaction called electrophilic aromatic substitution, or EAS. So what's happening is, in the first step, we want to make the electrophile. Our electrophile is going to be NO2 plus with nitric acid and acetic acid is going to form our new electrophile, nitronium ion. We call it as a nitronium ion, acetate and water. And if you are doing a traditional nitration, we normally use sulfuric acid and nitric acid. But in this one, we use acetic acid because it gives us a good result. Okay. Once the nitronium ion is formed, it is going to react with phenacetin by the following mechanism. So I will explain you this mechanism. I'll draw it with you guys. So you can see the pi bond of the benzene ring next to the amide group attacks the nitro group. Benzene ring is electron rich, act as a nucleophile. Nitro group, NO2 plus, electrophile. So it's going to attach to the second position of the benzene ring. And there is a mistake in this diagram here. You can see the positive charge is put on the carbon where you have 4 bonds. That's a mistake. But the positive charge on the benzene ring is supposed to be on the carbon of the benzene ring next to the nitrogen group. Okay, so this is not correct. So don't draw this structure when you're writing the mechanism. Okay, and I will show you how the mechanism works. Okay. And then what happens? The intermediate benzonium ion, we call it as the intermediate benzonium ion, which is the second structure, the middle one in this diagram. It is resonance stabilized. It can undergo resonance. Okay. And another product is possible from this reaction, 3-nitrophenacetin, that is not going to form by this procedure. Okay, and then we also want to look at now why it is attached to the second position but not the third position, and we have 2 substituents. Normally the direction of the electrophile depend on which group or the substituent on the benzene ring is more active, okay, or more predominant, okay. So the location of the nitro group in the final product depends upon the substituents already on the ring. So both amide group and acetate, that is the OCH2CH3, they both are considered activating. Activating means it gives more electron density towards the benzene ring. So the benzene will become more electron rich. And we call them as orthopara directors. Okay. However, the acetamide group, which is the nitrogen and the carbonyl group, is considered more strongly activating. As a result, the nitro ends up on the ortho to this group. Okay, if the acetate or OCH2CH3 group, OET group, is going to be more strongly activating than the other group, then the product will be formed at the ortho position, or the substituent will attach to ortho to that position. Okay, I believe we're going to be doing organic in this section about the phenol or the benzene aromatic chemistry. We'll talk more about it during that time also. Okay, so the nitro group will end up on the ortho position to the amide group. Okay, let me show you the mechanism, how it happens. Where's the PowerPoint? Okay, right there. Okay, over here. So this is our nitration. Okay, so I told you this mechanism is not correct. So let me go ahead and draw you how it should look like. So this is going to be your phenacetin, nitrogen. This is the amide group. And then you have benzene ring. And then you have your ethoxy group. Okay. Benzene is electron rich, and this is your NO2 plus. Nitronium ion, NO2 plus, electrophile. Normally sometimes we to represent a group of electrophiles we can put E plus. Okay, so the pi bond over here gonna go and attack the nitro group, and then you will see this compound forms nitrogen with the hydrogen, carbonyl group, methyl group, that is the amide group, and then on this side you still have that ethoxy group. And then you can see the pi bond on the benzene, 2 electron has been used to form a bond with the nitro group. And you know that benzene ring, though we don't write, there are hydrogens on each of these positions. Only the positions where you do not have any substituents. So here we didn't do anything to the hydrogen, so that is also going to be there. Okay, and over here on this carbon, did we have any hydrogens there? No, because it already saturated with the 4 bonds, the carbon. Okay, 1, 2, 3, 4. Carbon can hold successfully maximum 4 bonds without any charge. So 1, 2, 3, 4. Right now it has only 3 because the pi bond has been used to form a bond with the nitro group. So where do you think we should have our positive charge? Is it correct if you put it over here? No, because carbon is happy with its 4 bonds. So your carbocation or the benzonium ion would be formed, the positive ion, over here. So that is a mistake in this mechanism in the handout. But when you draw it, don't draw that. So draw this intermediate. Okay. And then what happens? After that, the next step is going to be we have water, acetic acid, nitric acid, they all have water, and you know we are in a very high concentrated acidic solution. So in acidic solution we never find strong bases like hydroxide. It cannot exist because it's not a base. So always in acidic medium it is the water that can act as a base. Okay, so not now. Okay, so you're gonna take water molecule. Now the next step, okay, next step is going to be regenerating the benzene ring and complete the process. So if you just leave the molecule like that, it's not going to be stable. Benzene would be very stable, when it has its all 3 bonds in place. So water molecule goes and grab this hydrogen, okay, and then the hydrogen carbon bond breaks and it gives its electron to form the pi bond back, okay, and when you do that you make this product, okay. You have NO2 and you got your resonance back, and then now the molecule is again neutral, and then you're going to be regenerating the catalytic acid hydronium ion, okay, which is your acidic species. So that is the mechanism for this reaction. And let's see how we are going to perform the experiment. You have to watch your virtual video, please do that, but I'll explain you what is the experimental procedure. We are also given the molar masses. Phenacetin 179 molar mass, 2 nitrophenacetin, 3 nitrophenacetin. They both have the same molar masses because it's a similar molecular formula, but only the position of the nitro group is the one that is changed. But there is a difference in melting points. Phenacetin 135, 2 and 3 nitrophenacetin, you have the nitro group at the second and the third position. So 2 nitrophenacetin has a lower boiling point 103 compared to 3 nitrophenacetin 125. Okay. And then the safety information, both the nitric acid, acetic acid, they are very hazardous. When you are handling any of these reagents, you want to make sure that you wear gloves, you put your goggles on, and then also you put a gown or a like lab coat if there is one. So it's simple, and then normally we keep the sash of the hood down so you would not inhale fumes. So you have to be very careful, okay? Okay, procedure. How are we going to conduct the reaction? You're going to dissolve about 5 millimoles of phenacetin. Again, we cannot measure millimoles from the balance. You need to convert it to grams, and you guys know how to convert millimoles to grams, and I would like you to show me that in your lab report, right, if you have forgotten. So 5 millimoles, and you need to know the molar mass 179. So let me remind you how you would do that. So we're starting with 5 millimoles, and then we need to convert this to grams using the molar mass. Normally the molar mass is given grams per mole, so you can convert millimoles to moles. How many millimoles are there for 1 mole? What is the milli stand for? 10 to the power 3 millimoles equals 1 mole. Okay, or 1 millimole equals 10 to the negative 3 moles. And then you're going to be converting into mass using the molar mass of phenacetin, that is 179 grams is 1 mole. So that would give us the mass in grams. Phenacetin is a solid, so we can use the grams. So 5 over 1000 times 179.895. 0.895. And if you round it to the significant figures, this is multiplication and division. What is the rule for the significant figures for the division and multiplication? You go by the lowest number of significant figures. So here we have 5. And these are exact numbers, you don't care. And then here you have 3. So we have to keep our answer in one sig fig. So that will make it. And then you also remember the rounding rules. 0.89. We are dropping 9. So you have to add 1 to 0.8. That will make it 0.9. So that's the amount you're going to be measuring. Okay. And then you're going to put it into a 125 milliliter Erlenmeyer flask. You add 5 milliliters, 5 millimoles, 0.9 gram. Oh, there are 3 significant figures, 5.00. Let me take that back. But you can, it's all right, 0.9. So there are 3 significant figures in 5.00, and there are 3 significant figures in 0.900 also. So 8 9.9, that's okay. Okay, and you add 20 milliliters of acetic acid. The molarity is given 17.4. That is the highest molarity that comes when you buy it from the store. And then if you want a diluted solution, then in the lab we dilute it using M1V1 equals M2V2. And you put 20 milliliters of acetic acid, and you're going to be adding a stir bar, and then you put it on the stirring hot plate which you have in the lab. And then we're going to let it stir until it completely soluble in acetic acid. So phenacetine will completely soluble at acetic acid, in acetic acid. And then you're going to turn on the mechanism, which is your stirring mechanism, and wait complete dissolution. Carefully add 1 milliliter of concentrated nitric acid. 15.8 molar, very high concentration, so have to be very careful at this point. You're going to be adding dropwise 1 milliliter. Okay, and at that time it needs more activation energy, so we give activation energy by heat. You're going to be increasing the heat about 40% in your heating knob, and heat for 10 minutes while you are stirring it. You will see all of this in your virtual lab. And then you're going to remove the reaction mixture. So at this point, we believe that the nitronium ion has been formed. Benzene ring is doing its electrophilic aromatic substitution in your solution. It attached to the second position to the amide group, and it's all done what we want it to do. Okay, and then you allow the reaction mixture to cool to room temperature, and at that time we didn't add ice yet. Okay, so after you are done with the 10 minutes, you're going to remove the reaction mixture and you add 60 milliliters of ice water. That's what we're going to be adding, ice, and you're going to swirl. So now what we do is we want the product to be form a solid. The solid is being formed by cooling down the reaction mixture, that is one thing, and also nitrophenacetine, and you can see it's an organic compound. And we did this reaction in acetic acid and nitric acid. Okay, and the reaction had taken place, so we want to make sure that organic compound precipitates or form the solid after doing the reaction. Just to make that happen, you lower the temperature by adding ice and water. And then remember, having water makes an organic compound crystallize out from the aqueous solution. Because we know like dissolves like, organic compounds will more readily dissolve in organic solvents. We have organic product, hydrocarbon, and then we have water. They don't have intermolecular interactions similar that would keep it as a liquid. So then your solid or your product will form a crude solid. Okay, and then afterwards we want to isolate our solid. It's with water and your bunch of acid components. So what you're going to do is you're going to filter it through vacuum filtration. You will see the vacuum filtration setup, and you guys may have already used the vacuum filtration also. So you filter it, and then you get the crude product. The procedure doesn't say so, but this crude product, normally when an organic chemist do a reaction, we always, if you want to get the pure product, the crude product is not the pure one, because it's right after the reaction had gone to completion. You have many unreacted nitric acid in it. You have many acetic acid and some other impurities that came along with your original reactants are all there now in your crude product. So the crude, we always, most of the time, you recrystallize it. So that is the method that normally organic chemists use to purify a solid, through recrystallization. What is the recrystallization? So from the first step, you already have crystals in the form of a solid. Now you want to remake those crystals. So recrystallization. You know that if you heat a compound, that would be soluble, but when you cool it down, sometimes it becomes a solid, right? So normally the temperature increases a solubility of a product. So what you do is, Now this nitrophene you add water to that. You take the crude product from the filter paper, you put it into another flask, you add water to it and you boil it. Okay, so meaning you have now a higher temperature. So at the higher temperature, your product, which is your crude nitrophene as well as any other impurities, will be soluble in the hot water. Okay, and then to make it little bit more soluble, because it is again organic compound, you can add a few drops of ethanol. Ethanol increases the solubility of organic compound, but not too much, otherwise it will not reform when you cool it down. But to increase the solubility, you add ethanol. So one popular solvent is water for the recrystallization, and then also ethanol water mixture is a good combination too. Okay, after everything is been completely soluble in the hot solution, you let it cool. You don't add too much water or alcohol, otherwise you will not get your crystals back. So you let it cool. So as the temperature comes to the normal room temperature, solubility of the solid will become less. So you will see the crystals start forming. Crystals of your crude compound will start forming, but any impurities that were soluble when you heated it up would remain as soluble. So they will not reform the solid when it cools down. Okay, now all the impurities are in the solution, but your crystals are looking much nicer now than the crude product, more defined. Sometimes you will see some more shiny, some crystals look like needle shape, some like plate shapes, some will create like a beautiful coral. So you can see those things, because then you're so happy, oh beautiful crystals, my compound is pure. Okay, and then afterwards we are still having our recrystallized product with a liquid, which is your water and ethanol. So now you have to do another vacuum filtration to isolate your compound, your crystals. Okay, and then you filter it again. You isolate your product in the filter paper and then let go of the filtrate, and then you dry this. And this will even dry faster, so you can put it in the oven, keeping the oven temperature less than the melting point of the compound, otherwise everything will be melted. Or maybe we can leave it for a week or so in the hood for it to dry through the air. Okay, so we can do that when we are performing experiments, but if you're really doing it in a lab, we will put it in an oven, okay, because we need the product quickly. Okay, so that's how the experiment is being done. Now you can watch the video and you will understand more what is happening in every step and the reason behind doing every step. Okay, any questions? Oh, I cannot hear you. Anyways, so pre-lab questions. Provide all of the reasonable resonance structures for the molecule shown below. Okay, so how do you write resonance structures? So let me take you to my place where I can write something. So the molecule is benzamide, right? That's what we had there, this molecule. So we have NHCOCH3, and this is the molecule. So how do you draw resonance structures? So your nitrogen has a lone pair on it. Okay, so the nitrogen can give its electrons to this bond to form a pi bond. And it should not stop there. If it just stopped there, what's going to happen? Carbon will end up having 5 bonds, which is not going to be happening. Okay, so then the pi bond next to that going to break and give its electrons to that carbon. So when you are drawing resonance structures, remember you have to put the double-headed arrow. So you're going to get a molecule like this, NH. Oh, okay. Now nitrogen has 4 bonds. Can we keep nitrogen like that? No, nitrogen should carry a charge now. What is the charge nitrogen going to carry? Plus. It's going to be positive. And these are the formal charges. Remember, you learned how to write the formal charge when you were little? right, in general chemistry 1. So just to remind you, normally how you find the formal charge, you get the group number of the atom. So nitrogen, what is the group number? Nitrogen is in, it's in the main group 5, right? Group number is 5. And then you subtract any bonds and any lone electrons on that atom. Now nitrogen, how many bonds are there on the nitrogen now? 1, 2, 3, 4. Do we have any lone electrons? No. So then 5 minus 4 equals plus 1. So the formal charge of nitrogen is plus 1. Okay. And then in the previous one over here, we don't have any charge on nitrogen. Now let's look at the formal charge of that also. Again, we are looking at nitrogen. Nitrogen group number is 5 minus the number of electrons and number of bonds on the nitrogen. So how many bonds are on the nitrogen right now? 3. Right? How many lone excuse me, how many lone electrons are there? 2. So 3 plus 2, 5 equals 5 minus 5, 0. So there should be no formal charge on the nitrogen. So we don't put anything. Okay? That's just a revision of how to find the formal charge. Okay. All right. Okay, so now you have this resonance structure, and then you can see here the pi bond. Pi bond opens up. Pi bond means 2 electrons. That's gonna go to this carbon. So you put that 2 electrons over here. Right? Sometimes you will see that the 2 electrons are being put over there. Sometimes you will also see that normally we put a negative charge to indicate that is electron rich, and that is the 2 electron negative charge. Okay. Still the molecule is charge balance. You have plus 1 and a minus 1. Okay. And then we can draw another resonance structure where this negative charge, negative 1 charge means 2 electrons, form a pi bond with the next bond, and then this bond opens up and goes to this carbon. 2 electrons is the alternate carbons that is carrying the negative charge. And then you can draw another resonance structure. This one, double bonds going to be there, nitrogen with the hydrogen, carbonyl group, cannot forget the positive charge there, and then this is still there. Now you have a new pi bond formed right there. So the neighboring pi bond breaks and gave its electrons to this carbon, forming another negative charge. So all of these are resonance structures. And then we can draw another one. This 2 electron goes to form a bond right there, a pi bond. And this pi bond opens up, give its electrons to this carbon. So now it gives you this structure. Pi bond there, another pi bond here, negative charge right there. Now you know what's going to happen next, right? NHCOCH3, positive charge. Now the next one going to be this negative charge gives to form a pi bond. So then the pi bond between the nitrogen and carbon opens up, gives its 2 electrons to nitrogen to reform your original compound, which is this nitrogen, oxygen. Now hydrogen is there, so the pi bond opens up, nitrogen got its 2 electrons back. Now there are no charges in the molecule. You reform your original starting material before we started doing your resonance. So the more resonance structures you have, a molecule is going to be more stable because the electrons are delocalized. Normally, rather than electrons being in one place, the delocalized structures are more stable. This is how the delocalization takes place. Okay. Now you remember when we were doing the nitration, we saw that the nitro group attached to this carbon. Now you can see the reason why, because during the resonance structure, this carbon carries the negative charge, not this carbon. Okay, so normally if you have a activating group like a amide group by donating electrons, the substituents would add to the ortho position or the para position, because this is the ortho position, this is meta, this is para. So the ortho position and the para position carry the negative charge. So activating groups on benzene would direct ortho para position for a substituent. But in our phenacetin, we had a methoxy group over here. Ethoxy group, not methoxy, ethoxy group. Okay, so it didn't happen here. Now the reason that there is a possibility it can go here is also because the methoxy group also electron donating group activating through the oxygen lone pairs. So it can also direct here. But between the amide group and the ethoxy group of phenacetin, amide is supposed to be more activating. That's why we have ortho position nitrated compared to this position. Okay. Okay, so that is the pre-lab question 1, to draw the resonance structures, and that's number 1. So you can draw all that resonance structures, draw with your own hand, don't use any computer models. The more you draw with your hand, you get more practice. Okay, provide a detailed mechanism for the reaction shown below. Now the same benzamide, we call that as a benzamide, amide group with benzene, nitration in the ortho position. So you need to give a mechanism how this happens. You can also refer to the mechanism that I showed you, how phenacetin nitrate to give the nitrophenacetin, but let's go ahead and do it together. Number 2, we have nitric acid and H2SO4 forming the nitronium ion and water, and then ortho position. Okay, got it. Let's go here now. Okay, so you have your group, benzene ring, nitrogen, HCOCH3. You're going to be reacting with nitric acid then. So with nitric acid HNO3 plus H2SO4, the first step of the mechanism is the formation of nitronium ion NO2 plus. So you form NO2 plus HSO4 minus hydrogen sulfate ion plus water. And nitronium ion is the one that's going to be electrophile. Okay, so write this equation also as part of your mechanism. And now the benzamide going to react with NO2 plus. Okay, and then how the mechanism take place. Pi bond gonna go and attack this nitro group, and then you will be making this compound NHCOCH3. So pi bond opened up, nitro group came here. Now where is the positive ion going to be? Which carbon? Carbon next to the nitrogen, NH, or the carbon next to NO2 group? It is this place where you're going to have the positive ion. So you want to draw the mechanism, right? So we are not done yet. So there is a hydrogen over here that was initially that you had over here. Remember, all these places has hydrogens. Though normally you don't write it, we should know that they are there. But the carbon that carrying the nitrogen, amide group, yes, don't have a hydrogen there. It is happy with its 4 carbon bonds. Now the next step, what is the next step going to be? We need a base to grab the hydrogen and reform the benzene ring. Can we have strong bases like hydroxide in acidic medium? Never, right? So what's going to be our base then? It's going to be the water. Water with the 2 lone pairs, perfect base. Okay, so this is your water with the 2 lone pairs. You're going to go and grab this hydrogen, and the hydrogen carbon bond breaks, gives its electron to reform your benzene ring. Now for this one you don't have to put the two arrows, the double-headed arrow, because we are not drawing a resonance. We're just drawing the reaction mechanism. And then nitrogen, hydrogen, carbonyl group form the pi bond back, and then we have our nitro group. So that is the mechanism, nitration of benzamide. Okay, that is B, part B. Earlier one was A. Okay, I hope you got it. So let's go back. So that is the detailed mechanism for the reaction shown below. Post-lab question, determine the theoretical yield and percent yield for the reaction conducted in this experiment. Okay, now this is our reaction. Phenacetin with nitric acid forming nitrophenacetin. Now, what is the molar ratio? If you had 1 mole of phenacetin having one nitro group attached, what is the number of moles of nitrophenacetin going to be? Going to be 1, right? 1 to 1 molar ratio. So if you can find out the number of moles that we use, it's the same number of moles of the product that you are making. And then you can use the molar mass of the product to convert it to grams. That is going to be your theoretical yield. Meaning, in theoretically, if the reaction had gone to completion without any side reactions or loss of products, that is the amount you should be theoretically making. But when you're actually doing the experiments, many things can go wrong, many human errors. You can spill your product, you can have stuff, stuck in your Buchner funnel, your filter paper, your flask. So that can lose the product, right? So that will give you less than the theoretical yield product in your actual yield. But the theoretical yield you can calculate even before you start doing the reaction, because you know how many number of moles we are using. So what's the number of moles we used? It is 0.9, remember? And also we need to find out the molar mass of nitrophenacetin, which is 244. And then we use 0.9 gram of phenacetin and 5 millimoles. So it's millimoles 5, 0.9 grams of phenacetin. So if you used 5 millimoles of your phenacetin, what's the number of moles of nitrophenacetin you're supposed to make theoretically? Same amount, 1 to 1 molar ratio, 5 millimoles, right? And then you're gonna multiply this by the molar mass of 2-nitrophenacetin 244 to find the theoretical yield. Okay, so the theoretical yield, so you have your phenacetin NHOCH3 with the nitro group, nitronium ion. You are making nitrophenacetin, and molar mass of this is 179 grams per mole. You start with 5 millimoles. So the molar ratio is the same. 1 mole of this will give you 1 mole of that. Start with 5 millimoles, then it's obvious we should be making 5 millimoles. Then we're going to convert that 5 millimoles into mass. So 5 millimoles, convert it to moles. 10 to the power 3 millimoles equals 1 mole. So this is how you calculate the theoretical yield, okay? Theoretical yield. 1 mole, and then use the molar mass. 1 mole forgot to put the nitro group. Nitrophenacetin is 179 grams. And that would give you the theoretical yield. So 5 over 1000 times 179 Nitrophenacetine, no, nitrophenacetine is different, not 179. 244 something. Let me recheck that. Yes, 2 nitrophenacetine 244. Okay, not 179. If I do a mistake like that when I doing it on the board with you guys, one of you will tell me, because you guys are so smart and I can do, silly mistakes like this, and I always welcome your feedback. We can have a good discussion together. I get all the information from you when we do it, but sad we cannot do that, but that's okay. So similarly, if you see some mistake that I'm doing while I'm doing, these presentations and in the videos, feel free to send me an email so then I can correct it with the whole class. I can do some mistakes like this. So it's 244, not 179. 244 grams. So 244 grams. Now we will have a different number. So the theoretical yield of nitrophenacetine would be 1.22 grams. Okay, and then in your virtual video you will find out what is the mass that they have obtained from this nitration reaction when they run the experiment. So your percent yield therefore going to be, percent yield is calculated as actual yield over theoretical yield times 100. You find the actual yield from your video and then you divide it by the theoretical yield times 100 will give you the percent yield. Okay, so you can do that calculation. And what else there to do? Okay, what are some possible sources of error in this experiment? What could lead to a lower percent yield? So watch the video again, look at the procedure. You can be creative, if you are actually performing the reaction. Because most of the time when you're doing a reaction first time all by yourself, many things can go wrong, right? We may not be measuring the correct amount from the balance, right? And you may not tearing the balance. And then when you're transferring from the weigh board to the flask, not everything will be transferred. There would be some left over. You might not be measuring the acetic acid 20 milliliters exactly, and then things can go wrong, like when you're adding nitric acid. You have to add it drop wise, so then the acetic acid in the solution and the nitric acid coming from the dropper can give you a nice nitronium ion. But if the rate of addition is different, you dump all the nitric acid at once, forgetting about that you need to add it drop wise, then your reaction can mess up, because all of these reactions involve kinetics. So it also need to control the how the reactants mix together to form the products, and also we need to change the thermodynamics, which is by heating the the reaction mixture. You may be heating too low, you may be heating too high, so then the reaction can go wrong, right? So these are some of the human errors. And then you might not be stirring the allocated time, and maybe when you're adding ice water, you're forming the crystals, and you can have your crystals formed, they're not completely transferred from the flask to the Buchner funnel, and then from the filter paper. So there are so many places that can go wrong in this type of reactions. So I just told you about many things, so you can grab those also, and then you can come up with some places what could make a lower percent yield. Okay, I think that's about it. So these are the pre-lab and the post-lab questions, and on top of this you also have to write a discussion, remember? So this discussion is going to be some of the theory that are already written in this background information, and so you can put them together and come up with a nice discussion. You can also use the same thing but do it in your own words, so then I know that you read it, you understand it. Now we are putting into your own words. Okay, understanding, you are doing it for yourself, not to make me happy, but I will be happy when you have a good lab report. Okay, all right then, I think that's it for now. If you have any questions, let me know. Okay, bye bye.